Welcome to Episode 3 of Road Ready. In Episode 2, we did in-depth diagnostics, looking for engine knocks and other troubles in the Jeep engine. There weren't any, so we concluded that this episode, we will be doing a major tune-up. So what is a major tune-up? For me, a major tune-up always begins with understanding the engine's condition. This is not about the knock that we pursued in the last episode. This has to do with any engine's condition before performing a major tune-up. So there are 4 basic things that any engine needs. Aside from adequate oil pressure and no knocks, the engine needs sufficient compression, proper valve timing, and proper valve lift. If the engine meets those 4 criteria, it can be tuned. To be blunt, it would be a waste of time and money to tune an engine or have an engine tuned that does not meet these 4 criteria. Tune-up consists of ignition and fuel system. We'll concentrate first on the ignition system after checking the condition of the engine. There is no point tuning an engine that is not in good condition. Once you've eliminated concern for knocks and rattles, you can move on. Oil pressure, of course, should be in a normal range for your engine. Consult the service manual for details. Every tune-up should begin with a relative or actual compression check. Here I'm showing the use of an Autel MaxiScope to enable a quick sense for cylinder sealing by running a relative compression test. This test measures starter amperage draw with an amp clamp. As the engine cranks over with the fuel and ignition system disabled, the starter load increases at each compression stroke. Battery voltage drops with the draw, and the amperage reading on the oscilloscope increases. That increased starter load for each cylinder can be compared. Starter amperage draw reflects the starter load or relative cylinder compression. This can be traced through each cylinder in the firing order. In this case, it's 153624 for a Jeep 4-liter inline 6-cylinder engine, and compared. No high variance is seen here. The cylinders are each pulling adequately and close to equally. This test is only accurate if the starter motor is in good condition. This is similar to the 720 Sun scope I have that was popular in the late 1960s. We could run a dynamic compression test by shorting each cylinder and seeing what the other cylinders were able to do with that load. On a very low budget, or if you're in the middle of nowhere, you can remove each plug wire individually and with a tachometer see what kind of RPM drop you have when you remove each spark plug wire. You are removing one wire at a time and putting it back in place before removing the next wire. The RPM difference shows you the load that cylinder was pulling, and essentially that's a dynamic compression test. A cylinder shorting test like I have described here can only be done above the RPM of the idle air control on late model engines. Otherwise, the idle air control will force the engine to have a stable idle speed. 1200 to 1400 RPM on a warmed engine would be an appropriate speed for doing a cylinder shorting relative compression check. You can see why I find it useful and far less time consuming to do the starter motor load test with the MaxiScope oscilloscope. This Autel tool is a fraction of the cost of most scan tools and is a really good diagnostic tool option. Visualize a tool that will measure voltage over time to test sensors, electronic components, electrical components, anything that can be measured with an interval of time and voltage. With an in-cylinder pressure transducer, you can even measure compression of an engine with the engine running. I will share a lot more about the MaxiScope when we get into advanced diagnostics and tuning. Although I do use a compression gauge, I use it prudently. Here I hold the throttle valve open to allow adequate airflow for filling cylinders during cranking. Tests with a compression gauge can be erroneous, and I'll explain why. While this OTC gauge is accurate and will give precise pressure readings, this is the engine pressure as the pistons move up and down at a rapid pace and can shove air into the gauge that would otherwise leak past the rings. Under cylinder firing loads, the piston may actually not be able to seal. The rings may not be able to seal against the cylinder wall. This is especially true when there is cylinder taper toward the top of the cylinder and the rings cannot seal as the piston reaches the peak of its compression stroke. For this reason, I would consider a compression gauge a relative compression test, and I rely strictly on a cylinder leak down test to diagnose piston ring wear, valve seat, valve face, gasket, and casting seal. The compression gauge will get you in the ballpark. The cylinder leak down test can pinpoint valve seat leaking, piston ring leaking or blow-by, cylinder taper, and gasket leaks. For the past 4 decades, I have relied on the Snap-on MT324 cylinder leak down tester for my diagnostic work. The factory recommended cylinder pressure should be 120 to 150 psi. Applying a traditional 10% maximum difference between the highest and lowest cylinder for reasonable cylinder balance, actual readings at 186,000 miles were 155, 152, 155, 145, 160, and 155, reading number 1 at the front to number 6 at the rear. Those following our engine knock diagnosis of a carbon buildup on number 5 cylinder should find the 160 psi reading not unusual. The spread between 160 and 145 is still within the 10% margin, especially if we allow for the carbon buildup and plan on removing some of that carbon. But number 5 cylinder is still suspect of having a carbon buildup. Attention is drawn to number 4 cylinder, and a leak down test might explain the 145 psi reading, which is slightly low. A good guess would be carbon buildup on the valves, which may be causing a slight amount of seepage at the valves and valve seats. I'd like to go into more detail about cylinder pressures from cranking compression tests and also the percentages of cylinder leak down that are acceptable. In my view, a range of 120 to 150 is pretty broad. That said, a 10% difference between the highest cranking compression and the lowest cranking compression is the limit. If the high cylinders were 150, the lowest cylinder would be 135. 135 in a modern engine like the Jeep 4-liter is frankly not great compression. I would want to run a cylinder leak down test on any cylinder under 145 psi. Regarding the cylinder leak down tests, I'm looking for 10 to 12% leak on an engine in really good condition. Up to 20% leak is acceptable if the engine is not burning oil. The spread between the cylinders should not be broad, and anytime you have a leakage that's measurable, you should pin down where the leak is from. Is it from the intake and exhaust valves? Is it the seal between the piston rings and the cylinder wall at the top of the taper where the highest likelihood of leakage will take place? Or is it a head gasket seepage? You'll want to pin that down if cylinder leak is over 20%. Despite the slight compression loss, this engine is a candidate for tuning. This engine does not use oil, but we will look inside number 4 and number 5 cylinders with a bore scope. There is no reason to suspect a valve lift or valve timing error, although if we were concerned, a vacuum gauge hooked to the intake manifold below the throttle body would be a good test tool to see whether there is an issue with valve timing, or a clear indication that valves are not seating, which would make for a shaky needle on the vacuum gauge. Let's look inside number 4 and number 5 cylinder with a bore scope camera before we proceed with the tune-up. Lowering the piston into the bore enables access with the camera probe. The aim is to see the piston crown, piston edges, cylinder wall, and the valves in the combustion chamber. This inexpensive camera comes with a mirror and magnet attachment. The mirror provides the angles needed to inspect the combustion chamber, valves, and upper cylinder ridge. if any, or look for factory crosshatch honing and any cylinder blemishes. An inspection like this will help determine the optimal time for complete engine rebuilding or simply doing an in-chassis ring and piston replacement with cylinder honing and a cylinder head sublet for valve service work. A borescope camera is not a typical pre-tune-up diagnostic tool. This carbon in number 5 cylinder has been an issue for some time. We're looking here at the crown of the piston and the combustion chamber and valve heads. Carbon buildup will increase the compression in this cylinder, which may account for the 160 psi reading. Carbon over time can damage valves, rings, and the piston. There's our culprit, carbon buildup, obvious on the piston crown. If we remove this carbon, the compression will go down slightly, probably to 155 like the higher cylinders. The detonation or ping will likely disappear. This is a classic case of carbon knock. Fortunately, we only hear it when the engine is idling. At other speeds and on the highway, even under load, we do not hear a knock. The knocking at an idle is due to the advanced timing and lane mixtures for meeting emission standards. The engine is not under load at an idle. Removing this carbon buildup would make a considerable difference. To sum up the pre-tune diagnosis, the engine is in good condition with some carbon buildup. Top engine cleaning using Seafoam motor treatment with SU-R&R equipment has removed considerable carbon. It would be smart to repeat that upper cylinder cleaning using the SU-R&R tools and Seafoam. The engine is now ready for the benefits of an ignition tune-up, so let's do a thorough ignition tune-up. See part 2 of episode 3 as we roll out the tools to get our hands dirty with tune-up work.